Okay, everyone, ready for some fun stuff? This is the coolest stuff in the world right here. Let's look at a sequence that we've already looked at before. The sequence 1 over n going from 1 to infinity, which is of course 1, 1/2, 1/3, 1/4, and so on. That's such an important sequence that we give it a name. It's called the harmonic sequence. I should know a little bit more about that, but I think it has to do with the fact that way back in the Greek times, it was involved in the lengths of strings for musical instruments and so on. And if you look at the Pythagoreans and some of the things they did with strings and such, I think you'll find some of this. So anyway, it's called the harmonic sequence. And so let's contrast that word with this other S word that I've mentioned, but now we're going to start talking about. It's called a series. And so in this case, we're going to take those same numbers, and instead of just looking at them singly, 1, 1/2, 1/3, and of course realizing that the limit of that sequence is 0, right? Because as n goes to infinity, those things are going to go to 0. Instead, we're going to add them up. So it's the same things, but we're looking at them not individually, but as an infinite sum or an infinite series. So I need to start with 1. So it's going to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/16 plus 1/17 plus 1/32 plus 1/33, and of course going on forever. And the question is, what happens when we add them up? Does that converge to anything? Now, as soon as I say converge, we're going to talk about this a little bit more later, but for right now, I'm just going to use what I'm sure you have a notion of convergence. Is there some number that this sum gets closer and closer to as we add them all up? And maybe I guess we should maybe start by giving another. This is called the harmonic. Let me just say it here. This one here is called the Harmonic Series. Okay, just like this was called the harmonic sequence, this is called the Harmonic Series. And anyway, well, let's just go ahead and answer that question. I won't get ahead of myself here. So what do you think? Is that going to converge to some sort of finite number? I know what I was going to say. I guess it makes better sense to compare it with something. Here we go. Let's look at this. This is a sequence 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/128, and so on. Same question for this one. This is another very important series. This one has its own name too. This is called a geometric series. Okay, because you basically take each term and you multiply that term by a number to get the next one. Okay, that's what a geometric sequence is. And this is a series because we're adding them together. So what about this one? Same question. Does it converge to anything, or does it what happens? And let's look at this one first. as I think about it, just to kind of show you that this is a reasonable question to ask. If you think of this as a couple pies, here we have one pie right here. So there's the first pie. Now we've got half of a pie, agreed? And then a fourth of a pie, and then an eighth of a pie, and then a 16th of a pie, and then a 32nd of a pie, and then a 64th of a pie, and I'm running out of room here, but you can see, hopefully visualize, that as this keeps going on indefinitely, I'm really just getting closer and closer to a total of 2 pies, right? It's kind of like you want to go to the wall, so you walk half the way to the wall, and then you walk half the way, and you walk half the way, and you walk half the way. You're never going to quite get to the wall. The point is you're never going to get beyond it, though. So your limit is the wall. That's what you're getting closer and closer to. So this thing right here just looks like, from this picture, that this series right here is going to converge to 2. And in fact, we're correct. Okay, we'll talk more about these later. But that one converges to 2. What about this one then? Does that have a finite number that it converges to, or not? What's going on? And the proof is just really, really cool. Let me show you, okay? And then we'll go on and talk about all this stuff in more detail. Look at here. Here's a 1. So we know that whatever this infinite sum is, it's got to be at least that big. Here's 1/2 right there. Let me write these down here. So we've got 1/2. So whatever this infinite sum is, it's got to be at least that big. Now I grab the next 2. Notice that if this were a fourth plus 1/4, 2/4 is 1/2. A fourth and a fourth is a half. Since this is a third, that means that the sum of these two things is a little bit bigger than a half. Agreed? The sum of these two things has to be a little bit bigger than a half. So now, whatever that sum was, let me get rid of this now. Whatever this sum was, it's got to be a little bit bigger than another half in there. Okay? Now, let's grab the next 4 of them. If this were 1/8 plus 1/8 plus 1/8 plus 1/8, I would have 4/8, which is another 1/2. But these are all a little bit bigger than 1/8. So these 4 taken together give me another amount which is bigger than 1/2. Okay, I'll just write bigger than 1/2 here. Bigger than 1/2 here. Do you see where this is going? Now I grab the next 8 of them. And by grabbing the next 8 of them, I end up at 1/16. Same argument as before. If all of these were 1/16, I would have 8/16. 8/16 is 1/2. But the others are bigger than 1/16. So this sum right there is bigger than 1/2. So there's another 1/2. Okay, can you do the next one on your own? This is 8 of them. Now I grab the next 16 of them. It ends up at 1/32. This right here has to be greater than 1/2 again. And there's no stop. I can keep taking just the next group is twice as big as the previous group, and each one of those will be greater than 1/2. And so as I go out farther and farther and farther, what's going to happen to this sum? Is it eventually going to happen? Let's see, where am I right here? 1, 2, 3, 3.5, and then I think I had another one, 4. Is it eventually going to be bigger than 4? Yep, it already is. Is it eventually going to be bigger than 14? Yeah, you go out far enough, and eventually it's going to be bigger than 14. You just grab 28 of these gobs here, and by the time you add them all together, you're going to be greater than 14. Will it eventually be greater than 140? Sure. Take 280 of them. Each one is twice as big as the previous one, so you're going to be going out there quite a ways by the time you take 280 of those things. But by the time you do, the total sum is greater than 140. No matter how large of a number you set, you'll eventually go past it. And that's what it means for anything to go off to infinity. Okay? What does it mean to say that the limit of x squared as x goes to infinity is equal to infinity. What does that mean? It means that you give me any number here, eventually you're going to pass it. Give me another number, eventually you're going to pass it. That's what it means to go off to infinity. Same thing here. Okay? So, you just learned some very important stuff just with these two examples. You've learned that if you add up a whole bunch of things, it's possible for that bunch of things to go off to infinity. It's also possible for that whole bunch of things, when you add them up, to converge to a finite number. Either one is possible. What determines which one happens? Okay, that's a qualitative difference. If it converges to 2 versus converging to 3, not a big deal. Converges to 2 versus converging to 30, maybe a little bit bigger deal, but still not a big deal. They both converge. But to go off to infinity means that it's never going to stop. It's going to break beyond any bound you put at it. So two totally different behaviors there. What determines whether it's this kind or this kind? And the key, and this is the key for the entire chapter now, let me make sure you see my eyes. The key is, how quickly do these things get small? Notice that these here are what? By the fifth one, I'm where? 1, 2, 3, 4, 5. Let's go to the seventh or eighth one. 1, 2, 3, 4, 5, 6, 7, 8. I'm at 1 over 128. 1, 2, 3, 4, 5, 6, 7, 8. I'm only at 1/8. These things here are getting small much faster than these. And that's the key. That's the key. It's exactly the same key that determined whether an infinite series, remember the infinite series we had? 1 over x squared dx from 1 to infinity. What happened there? The area underneath that thing was finite. Okay? What about 1 over, take square root of x as just an example. Same shape. But what happened? This one here, they both went to 0, just like these are both going to 0. But here you had a finite area. Here you had an infinite area. See that? And as you might already see, we're going to tie some really close connections between sequences and improper integrals that we've already done. Okay? That's the idea. So, okay. So, let's get back to the idea of what does it mean for a series, infinite series, to converge. What does it mean for an infinite series to converge? Well, I just had the integral up. We do exactly the same thing with series that we did with integrals. What did we do with integrals? We basically said, what does it mean to say that this thing, what does this even mean? What does that even mean? Because we defined an integral to be something on a finite interval. So what did we do there? We broke it up into two different mathematical ideas that we had already defined. We had already defined what this means. No problem there. And we'd already knew the idea of a limit. And so that's what we did. We put those two together and we said that these two things together is what the definition of this is. And now we're going to do exactly the same thing with a series. We're going to say, okay, I know what it means for a sequence to converge. And so we're going to, just like we did here, I'm going to write a series as a sequence. Okay, a sequence, you have to have little commas between each one. So here's what we do. This thing right here in order to ask whether it converges or not, we write this as a sequence of partial sums. Let me show you. There, we write it like that. See this? This is a partial sum. It's not the whole infinite sum. It's just the sum of the first one of these things. Comma. Here's the next term in the sequence. The next term in the sequence is the first two of these things. The next term in the sequence is the first three of these things. The next term in the sequence is the first four of these things. So now, notice none of these things is itself going to infinity. They're all finite, okay? Just like this integral from 1 to b was finite, okay? No problem there. And then same as we took the limit of this thing as b went to infinity. Now, here's what I'm going to do. I'm going to say that this thing right here is equal to S1. That's the first partial sum. This is S2. That's the second partial sum. Here's S3, the third one. Here's S4, the fourth one, and so on. And then, just like we did here, we're going to say that this thing converges means, it means that the limit of the SNs as n goes to infinity converges. Okay, that's what this means. To say that this thing converges means that this limit right here converges. Okay, and so also then, whatever this limit is, if this limit here, as n goes to infinity, is equal to, let's say that that limit is big capital S, then we say that this thing right here converges to capital S. Okay, so in practice, we'll do this to some extent, but this is what it means. This is how we think of and define for an infinite series to converge. Okay, we look at the partial sums and we break it up into things that we're already familiar with, namely sequences and the limit of a sequence. Okay, very good. So now let's apply this to some other problems. As I erase this, I think to myself, I think that's about as good of an explanation as I've ever given. And here I'm giving it just to a computer monitor rather than to a class. Wow, how much better I could have lectured all these years if I just didn't have any students in the class. But anyway, hopefully you're all catching on as you watch this. So let's do an example. Let's go back and right away and generalize from the one we had of the pies with the 1/2. This is the more general geometric series. So this is equal to 1 plus r squared plus r cubed all the way out. So let me write it again. It's called a geometric series. Okay? It's a value of r in there now. So it may well be that whether it converges or not depends on what r is. In particular, let's just look. If r is equal to 1/2, then we have the same thing we had before. We had 1 plus 1/2 plus 1/4, and it certainly looked like that converged to 2. Okay? On the other hand, if r is equal to 3, then what are we going to get? Then what's this series going to look like? It's going to be 1 plus 3 plus 3 squared is 9 plus 27 plus 81 plus 243, okay? Well, holy smokes. This series certainly does not converge because even the individual terms are getting big. You put them all together, and there's no way that they are going to add up to a finite number. Whoops, I want to make sure I still working here. Okay, very good. Okay, so whether it converges or not depends on what the value of r is. So we need to figure out for what values of r is it going to converge. Okay, so here's what we do. Kind of a neat geometric trick. Watch this. Here's what we do. First of all, we look at the partial sum. So we're going to look at 1 plus r squared plus r cubed plus r to the fourth, all the way, let's say, up to r to the n. Okay, so there's the partial sum that goes up to r to the n. Okay, and then we're going to do something kind of clever. We're going to multiply that by 1 minus r. Okay, no reason you would think of doing this now, so you don't have to at this point wonder why did you know to do that. I knew to do it because I've read calculus books before. So just follow along and see if you just don't agree with where we're going. Okay, so what happens if we were to multiply this all out? Well, let's do it. You multiply 1 by all these things, and you also multiply negative r by all these things. And what I want to impress upon you is that by the time you do that, you get what's called a telescopic series. Telescoping, we'll call it a telescopic sum. What's a telescope like? You have this big telescope, this big spyglass that's extended, and you push it all back together, and all you've got is the eyepiece here and the the final piece here. So all those other things all kind of fold in between. Same thing happens here. Okay, watch what happens. You're going to get 1 times 1, which is 1. Here you're going to get 1 times r, which is r, but that's going to cancel with this negative r. See that? Then you're going to get 1 times r squared, which is r squared, but that's going to cancel with this negative r squared right here. Then you're going to get a positive r cubed, but you're going to get a negative r cubed. You're going to get a positive r to the fourth, but you're going to get a negative r to the fourth. So all those middle ones all cancel out because you have a positive and a negative which cancel. So the only things you're going to have left by the time you do all this multiplication is just this very first one, which is 1 times 1. And can you see the other one that's going to stay? It's going to be this very last one that you get by taking r times r to the n, which is going to be minus r to the n plus 1. See that? So that's what happens when you multiply it out. And now, just to save board space here, I'm going to divide both sides by 1 minus r. Okay, we're going to have to assume here r is not equal to 0. Okay? If r was equal to 0, then the sum is easy, right? It's just going to be 1. 1 plus all these things is assuming that we're saying 0 to the 0 is 1, and then all these other things would be 0. So for all this, we're assuming that r is not equal to 0. So we've got this. So notice that this is a partial sum here, right? This is what happens when we just take the first n plus first terms of this thing. And so now what we're interested in is what happens as that limit goes to infinity. So whatever this sum is, let's go ahead and do it. Let's say that this equals s, whatever s is going to be. I'll just put an s right here then. So s is going to be equal to the limit of all these things as n goes to infinity, and that's going to be the limit then of this thing. as n goes to infinity. And now we can rely on what we did in the last section, okay? What did we learn? We learned that if r is some number greater than or equal to 1, that this thing, or greater than 1 in particular, if it's greater than 1, then you take anything greater than 1 in size and you keep multiplying it by itself over and over and over and over again. This thing is going to diverge. This thing right here will diverge. So this thing here will diverge. Whatever this big number is going off to infinity, subtract it from 1 and divide it by some constant number, is still going off to infinity. So the point is, this thing is diverging if r is in size is greater than 1. On the other hand, that's bad news, I guess. The good news is, if r is less than 1, then what did we also learn? We learned that you take any number less than 1 in size, absolute value is less than 1, and then this thing not only converged, but it converged to 0. So if r is less than 1 in size, this whole thing goes to 0, and I end up with a really nice answer, 1 over 1 minus r. This is if r is less than 1 in size. So if r is greater than 1 in size, this happens. If r is less than 1 in size, that happens. So we've got almost all the answers here. All we have to do is worry about what happens when r is equal to 1. We can do those independently. If r is equal to 1, you're going to get what? 1 plus 1 plus 1 plus 1 plus 1. That's just going to get as big as you want it to get. That's going to diverge. So it's going to diverge if r is a positive 1. What happens if r is a negative 1? What happens if r is negative 1? You're going to get 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. What do the partial sums look like? The first partial sum is 1. Then by the time I add the first 2, the partial sum is 0. Then by the time I add the first 3, the partial sum is back to 1 again. Then when I add the first 4, the partial sum is back to 0. Then 1, then 0, then 1, then 0, and so on. So these partial sums don't converge. They just keep jumping back and forth. So it diverges there as well. There's no limit. So there we go. It was good. I put it on there a little prematurely, but the point is for r either equal to 1 or negative 1, this thing is going to diverge. So that's a powerful, powerful result, both in and of itself and for a lot of other things that we're going to get from it. Okay? That's why I did it right from the start. Now, in fact, as long as I did that one right now, let's go ahead and do some other things as well. Let's put this result right up at the top here. And say that this thing is equal to 1 over 1 minus r if r is less than 1, and it diverges if r is greater than 1 in size. Now notice something as I write this, just a little bit unfortunate about mathematics. We use this symbol right here to stand for two things. Let me contrast it. When we had this series right here, this sequence right here, this was the sequence, right? That was the sequence. And then if we wanted to say what does the sequence converge to, then we wrote the limit of the sequence as n goes to infinity is equal to 0. And so we have two things. Those are the things themselves. These are what they're getting close to. When you get a series like this, you use the same notation to stand for both of them. Okay, as I say, it's a little bit unfortunate, not a big deal. But this thing right here, r to the n, it stands for just this right here. It stands for that, just like this does, but it also represents what the final limit is. So I can either write it out like this, and it's also proper to say this is equal to what I have up there. So you use the same thing both to denote what's going on, and you also use this to denote what the actual limit is. Okay, we don't use another thing to say this is equal to s and s is equal to this. So anyway, if I hadn't mentioned that, you would have probably never even thought about it. But just trying to be honest with you. Okay. So let me make sure that everything is visible there. Very good. Okay, so let's do a couple other problems just to show you what you can do with this. Here's one right here. Okay, the challenge is to find if that thing converges, and if it does converge, what does it converge to? Okay, and I'm going to use this as an example to without going into all the formalities of, well, here's the properties of limits and here of sequences and series. I'm going to just apply them right here. I haven't spent time saying that the limit of the sequence an plus bn is equal to the limit of an plus the limit of bn. Those things apply to sequences and series just like they applied to functions, okay? And because a sequence is a function, so it would apply to it. And a series is just a sequence of partial sums, so it applies to these two. So let me just show you how it works. The point is I can break up this numerator like this. Agreed? This over this, and this over this. So that's just algebra. But now I'm going to go ahead and say, hey, since this is a limit, I can use my properties of limits, and I can break it up into two and write this as 4 over 5 to the n plus the infinite series of 3/5 to the n. And I'm going to get a little sloppy here. All these things, I'll just go 0 to infinity, like that. And then I just also, if you want to, you can go ahead and factor the 4 out. So here's the 4, that's a constant, comes out front. I'm going to write this as 1/5 to the n plus the series of 3/5 to the n. And again, the key here is that they both start at 0. Now we can go ahead and evaluate each one. What's this going to be? 4 times. What does this say? It says it's going to be this sum here sums to 1 over 1 minus 1/5. Right there. And how about this sum right here? It sums to 1 over 1 minus 3/5. Okay, now just a little bit more algebra. This is equal to what? 4 times, let's see, this is 1 minus 1/5 is 4/5. 4/5 on the bottom is 5/4 up on top. So this cancels with this, and you just get a 5 there. What happens here? This is 1 minus 3/5 is 2/5. 1 over 2/5 is 5/2. So you get that. So here's 5 plus 5/2, which is 10/2 plus 5/2 is 15/2. There you go. I think I did that correct. Okay, so there you go. Isn't that cool? So there's one. Let's do another one involving geometric series. Okay. This is such fun stuff. Let's try this one, just to show you some tricks of the trade. 5n over 3 to the 2n plus 1. 5n over 3 to the 2n plus 1. Okay, what can we do there? Well, let's see. This is what we know. Can we get it in that form? Sure we can. It just takes algebra. I say just, but I realize as I say that that's the main problem that math students have in the world these days. So I can do this. I can write this as 5 to the n, and I can 3 to the 2n is equal to 3 squared to the n, right? Because you multiply those and get 2n. 3 squared is equal to 9 to the n. So this is, and then you also have a plus so 3 to the 2n plus 1 is equal to 9 to the n times 3 to the 1, because you can, this thing, this right here is 9 to the n, and then the plus 1, you can, let me do it one more time, doggone it. Okay, 3 to the 2n plus 1, I'll write as 3 to the 2n times 3 to the 1. Okay, you can do that first. Then I can write this as 3 squared to the n times 3, which then is 9 to the n times 3. So the point is, I can bring this 3 out front, and now I just have a 9 to the n right there. See that? So the 3 comes out, 1/3 comes out front, and I've got that. And so now I've got is equal to 1/3, and I can write this as 5/9 to the n going from 0 to infinity. And now again, it's just algebra. It's going to be what? 1 over 1 minus 5/9. 1 minus 5/9 is 4/9, so it's going to be 9/4. This goes with this, and I get a 3 up here, so it's going to become 3/4. 3/4. See how that works? And I just thought of another one that's not in my notes, but let's do it anyway. Let's do this one. Let's go back to our 1/2, just as a simple example. 1/2 to the n. Let's go n going from 3 to infinity. What if we start at 3 rather than 0? How does that affect things? Well, do you agree that starting at 3 is equivalent to this series right here? They both do exactly the same thing, right? This one, when you start at 3, it's 1/2 to the 3rd, then 1/2 to the 4th, 1/2 to the 5th. When n starts at 0, it's going to be 1/2 to the 3rd, then 4th, then 5th. Exactly the same thing. So now you've made it like that previous problem, right? So now you can just write it as 1/2 to the n times 1/2 cubed, and you bring and this is going from 0 to infinity. 1/2 cubed is going to be 1/8, and then times this, and then you're going to get 1/8. 1 over 1 minus 1/2, which is 2. 2 times 1/8 is 1/4. There you go. Okay, so good. There you are. There's a good introduction to geometric series. Let's try another one. How about this one? How about that one? Well, yes, well, it might occur to you that this thing here, if you were to multiply out the bottom, it would look like this. Agreed? And it might occur to you that back a couple sections ago, when we looked at improper integrals, when we looked at something like this, we showed that thing converged. Okay, we basically did the p-test on this one. That was a power greater than 1, so that converged. And this thing here is the denominator is bigger, so the fraction is smaller than this. So this thing also converged. So is there any relationship to this thing converging or diverging, and whether this thing will converge or diverge? I'm not going to answer that question right now, but I just want to prime your thinking, because that will be what we discuss in the next lesson. Okay. So anyway, back to this one. Let's do something else that's kind of clever with this. Okay. This also goes back to what we did before. This is why I like Calc 2 material so much. Let's take this, and does this remind you of anything else that we've played with? Looks like that. When we had an integral like that, we used partial fractions on it. Let's do the same thing here. We'll get that. And then we'll multiply it out. We're going to get a times n plus 1 plus b times n. And then by letting n be equal to 0, we're going to get a is equal to 1. Right? If n is equal to 0, boom, boom, you're going to get a is equal to 1. If n is equal to negative 1, that makes this go away. You're going to get negative 1 times n is equal to 1, so b is equal to negative 1. Okay? Then you check that out on your own again. If n is equal to negative 1, you're going to get negative b is equal to 1, so b is equal to negative 1. So this thing here is 1, this thing here is negative 1. So in other words, here, if I wanted to, I could write this as 1 over n minus 1 over n plus 1. That's just algebra. I haven't done anything fancy calculus-wise with that at all. I've just rewritten it using my partial fractions. Okay? But let's watch to see how that helps. Because now, what happens when I take those terms? When n is equal to 1, it's going to be what? 1 minus 1 half, agreed? Then, when n is equal to 2, it's going to be 1 half minus 1 third. Then, 1 third minus 1 fourth. Then, 1 fourth minus 1 fifth. Keep on going. And finally, I guess I can do it up here, 1 over n minus 1 over n plus 1. Okay? And it goes on from there. So, this would be the nth partial sum right here. The nth partial sum is what I get by adding up the first n of these things. And let's see once what happens when I add up the first n of them. Okay? I add up the first n and look what happens. Here's this nice word telescoping that comes in again. See this? Boom, boom. That's one of the fun parts about calculus is you can go boom, boom every once in a while. Boom, 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 all the way through, boom, boom. The only things you're going to have left is going to be the 1 minus 1 over n plus 1. See that? So that's the nth partial sum. If I add up the first n of these things, it's going to end up to that. And so I'm interested in what this thing goes to. So all I'm interested in is what's the limit of these partial sums as n goes to infinity. And as n goes to infinity, boom, that all goes to 0, and you're going to get 1. So in other words, these things converge to 1. So it's kind of nice. We not only know that it converges, similar to indefinite integrals again, or I should say improper integrals, integrals that went off to infinity. Okay? There's two questions we have. Does it converge or not? That's the most important question. And then if it does converge, if possible, we want to know what it converges to. Not always are we able to, but if we can, all the better. And here, we not only found out that this thing converges, but it converges to 1. Okay, one more problem. These are all, I chose ones that each one has a good lesson behind it. And here's the last one I want to do for you. It is n over 2n plus 5. What about that one? What about that one? Does that converge or not? Well, if you were to write out the first few terms of it, that's sometimes helpful. If n is equal to 0, you're going to get 0. When n is equal to 1, you're going to get 1 over, 7? And then 2 over 9. Right? And then 3 over 11, and so on. Did I do that right? Let's see. Yep, that's right. What's going to happen as n gets bigger and bigger and bigger? Well, let's look at the individual terms and see what happens. Notice that this thing right here, as n gets big, this goes back to what we did in the just a section or so ago. We can divide both the top and the bottom by the highest power of n on the bottom. And when we do that, we're going to get the limit of 1 over 2 plus 5 over n as n goes to infinity. This goes to 0, goes to 1/2. So what we know is that these individual terms are getting closer and closer to 1/2. As you go out farther and farther, when you hit 100, what are you going to have? 100 over 205. See that? They're going to be pretty close to 1/2. By the time you get to 1,000, it's going to be 1,000 over 2,005. Very close to 1/2. Agreed? So it's as if you just keep adding up 1/2 as you go farther and farther, 1/2 over and over again. Okay, so does that make sense to you? Clear that this thing is going to diverge because these individual terms are not going to 0. Okay, even when the individual terms went to 0, like here, the harmonic series, we weren't guaranteed that it would converge. This thing here went off to infinity, even when the individual terms went to 0. Okay? If the individual terms don't go to 0, it has no hope of converging because you're adding 1/2 each time. And so the infinite sum is just going to go off to infinity. There's no way that the infinite sum can converge if the individual terms don't go to 0. So let me write that as a theorem right off the bat here. Okay? Here's the way to write it. If the individual terms do not go to 0, then this series must diverge. Okay? If they're all positive, it's just going to go off to infinity. If those individual terms alternated between 1 and -1, for example, then it's going to do the same thing that happened when we looked at this series. It's just going to jump between 1 and 0 over and over again. Okay? The point is, if the individual terms aren't going to 0, there's no way that this series can diverge. The only way it can diverge is by these as you go farther and farther, the increments, the things that you add on have got to keep getting smaller and smaller and smaller. Okay? Let's see. I don't know. Is it worth proving that? Maybe so. Let's just prove it a second. Here, let me first give you a quick lesson in logic. Okay, I live here in Michigan, in Holland, Michigan, and Detroit is over on the other side of the state. So let's just make this statement: if in Detroit, then in Michigan. Everyone agreed? I think there's only one Detroit in the world, on the east side of the state of Michigan. So if you're in Detroit, then you're in Michigan. That's a statement. And that statement is true. Okay? Once you have a statement, you can switch the if and the then around. If in Michigan, then in Detroit. Is that true? Obviously not, right? You can be in Michigan without being in Detroit. This is called the converse of the statement. And let me get rid of that just so it's clear. And this converse is not necessarily true. It's false. Okay? Another thing you can do with this statement is, I've heard it called the inverse. That goes all the way back to my high school days. Okay? You take this original statement and you put a not in front of each one. If not in Detroit, then not in Michigan. True or false? That's also false, agreed? You can not be in Detroit, but you could still be in Michigan, so that's false. And finally, you can put these two together. You switch the if and the then around, and you also put a not in front of each one. That's called the contrapositive. Contrapositive. Okay? So what does that read? If not in Michigan, then not in Detroit. Aha! Do you agree that that is true? If you're not in Michigan, there's no way you can be in Detroit. That's true. And that is a quick lesson in logic that the statement and the contrapositive are logically equivalent. This one is true if and only if this one is true. Okay? They stand or fall together. Okay? So that is very important in mathematics, because sometimes you'll use a statement one way and sometimes it makes more sense the other way. So what would be the contrapositive of this statement? It would be what? If, what's the negation of this? If it doesn't diverge, it would converge. If this thing converges, then the individual terms must go to 0. Okay, this is just shorthand for saying that the limit of an as n goes to infinity is equal to 0. Okay, you write it like that. Okay, the individual terms go to 0. So those are both true. Those are both true. And I guess the proof could be something like this. Let me just think about it here. Okay, if this converges, then Sn is equal to the sum from A1 to A sub n, and S sub n plus 1 is equal to A1 plus An plus An plus 1. So, if this thing converges, if this converges, that means that the limit of Sn converges to, let's call it S, and this thing is going to converge to the same thing because it's just one ahead of this, but they're both converging to the same thing. So this limit is equal to S. So the limit of Sn plus 1 minus Sn is equal to, you can break it up into each one, so this limit was S and this limit was S, which gives you 0. But the difference between this one and this one is just, if you take Sn plus 1 minus Sn, you just get An plus 1. So the limit of An plus 1 is equal to 0. So if you want a nice formal proof, there it is. To me, it makes more sense just to think about it. If the individual terms don't go to 0, there's no way the sum can. Okay? But those are both true. Okay? What about the converse of this? So these are both true. What about the converse? Remember, the converse may or may not be true. We can't get it logically, but maybe it's still true. The converse would be what? If An goes to 0, then the series converges. Is that true or false? True or false? Okay? Your answer to this question will show whether or not you've internalized the things I've said up to this point. And I just know from experience that even though I tried to make it really clear over and over again, a lot of people it just doesn't absorb, okay? So here's what you should be thinking. If the individual terms go to 0, then does this converge? The answer is no. We've got an example. That's why the harmonic series is so important, because it's a great example among many, many others, that even though these individual terms are going to 0, they aren't going to 0 fast enough. When you add them all up, the thing still diverged. Okay, this still diverged. They aren't going to 0 fast enough. So so that's what we're going to get into. That's what we're going to get into in the next lesson, is determining a whole lot more which series converge and which ones diverge, and it's all going to depend on how fast they go to zero. Good stuff. Good stuff. Okay, very good.